Materials for optical absorption can be engineered for detecting light of a particular wavelength or efficiently absorbing sunlight, while materials for optical emission can be engineered for efficient lighting. A photon of light is absorbed or emitted when a single electron moves from one state to another. We talked about how the energy of the transition gives the photon its energy, so delta E equals h bar omega. The photon also gets its momentum from the electron transition, but it is so small the transition looks nearly vertical in an E versus K diagram. The photon also has angular momentum that it can easily get from the orbitals in a solid, but this also makes SP and PD transitions higher absorption. The lowest energy transition will be exactly at the band gap energy, but there is only one state, so the intensity of absorption is low. At slightly higher energy, there are more electrons, a higher density of states, that can make a vertical transition in the E versus K diagram, so the absorption increases rapidly with some slope. For an electron to move to a state with a different K, there must be another particle involved so that the overall momentum is conserved, like the collision of two billiard balls. Traveling waves of atom vibrations, such as sound waves, can also carry momentum. When they behave as particles, we call them phonons. When an electron-hole pair is excited across the band gap in an indirect semiconductor, a phonon is either created or absorbed that compensates for the change in electron momentum. The phonon creation or absorption will also change the energy of the photon that is absorbed, as required by conservation of energy. But the energy of phonons are typically less than 0.1 eV and often not noticed in the absorption spectra. The requirement of the additional particle decreases the probability of absorption, so the absorption coefficient for indirect transitions is orders of magnitude smaller than for direct transitions. At higher energies, the absorption coefficient increases at first because there are many more possible indirect transitions, and then when the energy of direct or vertical transitions is reached, the absorption coefficient increases rapidly. The lattice vibrations or phonons themselves can also absorb and emit photons. Because ions in a solid are also charged particles, they easily couple to electromagnetic radiation. Because the phonon energies are in the milli-electron volt range, the photons that couple are in the far infrared. The absorption coefficient of various semiconductors are compared here as a function of wavelength. You can spot semiconductors with direct band gaps as they have much sharper absorption. Silicon makes a good window for infrared cameras as they absorb visible light but let infrared light transmit to the detector. The indirect band gap makes silicon less absorbing to visible light than gallium arsenide, so thicker silicon wafers are needed than gallium arsenide for photovoltaics. After an electron is excited, it eventually relaxes back to the ground state. Fluorescence is the immediate re-emission of light, usually of similar or lower energy. Both the electron and hole can reduce their energy or thermalize by giving some energy to lattice vibrations or phonons. If the electron or hole flips spin or wanders off to where it is more difficult to relax back, the process can take much longer, producing long-lived phosphorescent light. Efficient, useful phosphors for luminescence often utilize electronic defect states. Structural defects like vacancies, interstitials, or substitutional point defects disrupt the electronic band structure locally and can lead to electronic states localized around the defect. The energy of these defects can be in the band gap, like electron donor or acceptor defect states. The luminescent electron transition that produces light can be between the defect states or between the band and defect states. Sometimes the defect states are called recombination sites because they facilitate the recombination of electrons and holes. Defect states can also act as trapping sites where the mobile electrons or holes from the bands can go but then become localized and no longer transport charge. After some time, the electrons or holes can be thermally excited back into the band and luminesce, extending the time of luminescence. Luminescence can also be initiated by other high-energy processes, such as bombardment with high-energy electrons, X-rays, or gamma rays. LED lighting is posed to take over the lighting market because they are more efficient than conventional lighting, even fluorescent lighting. To get a broad spectrum of white light, phosphors are typically used. A common example is the use of a single blue LED, which not only provides blue light, but also excites a cerium-doped yttrium aluminum garnet phosphor, which has a broad band yellow emission that combines with the blue to produce white light. The polymer droplet acts as a lens to focus the light and protect the phosphor.